All right, so I'm going to do my best to explain this problem here, but basically it's a problem about planes containing a line and at 30 degrees to a given plane. So I'll just read out the problem. It says, find the equation of a plane that contains the line r of t equals this and makes an angle of 30 degrees with the plane 3x plus 3y minus the square root of 6z equals 5. Obviously the solution's here, but I think it's quite in-depth knowledge about vectors here, so I wanted to sort of visualize it and hopefully make it make some sense for us. Okay, so there might be a bit of pausing and me thinking here, but basically the question says give your answer in the form ax plus by plus cz equals d, and then I was just looking at my solution here, and it's not in that form, but obviously if you expanded things out and collect like terms and then move them to the other side, you could get it in that form, so just something to be mindful of there. Anyway, I think it's really important that we try and visualize this. So the first thing I'm going to do is I'm going to visualize this line r of t. So r of t over here, if I minimize that, r of t is this line, I believe. You can see that it's sort of situated in 3D space like that. Okay, and we've got some point 0, 2, 1. So that's this point here. And that point is on that line, as we can see. Okay, we also have the direction vector. If we really wanted to, we could take the direction of this line r of t, which would be negative 4, 4, 3. And the plane that gets given in the question is 3x plus 3y minus the square root of z equals 5. So that's this plane here. So I'm going to put that in pink. And basically, what our sort of big picture stuff, the question is asking us, find two other planes that contain this line that are at 30 degrees to this pink plane. And there's two solutions to it. There's two solutions that sort of fan out in this direction from that plane to give you both the solutions that we're looking for. And then the question is, how do we do that? So if we come over here and have a step through it, basically what we need to do is we need to find the normal of the original plane. So again, a bit of in-depth vector knowledge here, but the normal to this plane, you just take the coefficients of each part and that gives you a vector pointing in the direction that the sort of plane is facing. So you get the vector that would be 3, 3 multiplied by the square root of negative the square root of 6, I should say. And then what we're going to do, the required normal. So what we're going to say is we need the normal to the direction vector d. So the direction vector d is basically a line that points in that direction. We want to know what is the normal to that line. And so we take the dot product between them. So vector n is ABC dotted with vector d. D is this one. So we get negative 4 times A plus 4 times B plus 3 times C. So that will be our dot product between them, and we let it equal 0. And then you can see we've got a simultaneous equations. Sorry, we haven't got simultaneous equations. We've got an equation with 3 variables, but we can't solve that obviously because we've got one equation, we've got 3 variables. So what we can do in 3D sort of vector geometry stuff is we can just pick an arbitrary case and just make life easy for yourself. So just let C equals 0. So if we let C equals 0, we get negative 4A plus 4B equals 0, in which case A equals B. And so subbing that back in here, we're just picking the simplest case. If A equals B and C is 0, well, you can just pick the coordinates 1, 1, 0. So if we go back over here, we should have that somewhere. Okay. And so we think about what that represents. If we put the direction vector in, these are at 90 degrees. So this vector here is the direction vector of this line. And you can see if I just do the angle here, that is at 90 degrees to that. So basically we found the vector that is perpendicular to this direction vector, or perpendicular to that line which has this direction vector, I should say. Okay, so that's handy. And then what we need to do is at the moment we're just trying to find the plane that would contain that line, right? So what we do from there is we use the point normal form, okay? And again, this is in-depth vector knowledge, but I'll put a link where I've explained this before. We take the vector n, so 110, multiplied by r minus r naught, and that has to equal 0. And that basically tells you r naught is a point, so that's this point here, point A, and r is our direction vector here. And you do that and you'll get x plus y minus 2 equals 0. Now this question is fascinating because that plane is this plane here, and sure enough, well actually not sure enough, but that blue plane does go through that line, which is interesting. And so actually we know that it should have gone through that line because that's the conditions that we set up. But interestingly, if we take the angle between here and here, that's 30 degrees, but we didn't put that restriction on it yet. This question is kind of nice in a sense that when we sort of find that simplest plane that contains that line, we end up with one of our answers already. So one of our answers is x plus y minus 2 equals 0. But we know that there is two solutions. And this is where we're going to move to the next part, where we say this. So the angle between two planes is obviously the angle between two normal vectors that define those planes. And so what we can do is we can use the dot product, or the expression of the dot product. We remember that cosine of 30 degrees is plus or minus root 3 on 2, and then that's equal to this. We've already done the positive case. Remember, cosine of 30 is root 3 on 2, cosine of 30 degrees, or cosine of pi on 6 radians is root 3 on 2. So we actually need the negative case here, so we're going to think about the negative case. And we'll get a second normal. We're trying to solve here. We already know what n1 is. We already know the plane that we're interested in. So we're trying to find this n. And if we do that, we will get this. Okay? And then again, we need to use the point normal form with a. So we need to do n multiplied by r, which is our direction vector of our line, minus a point on that line, which is a. And then you'll get this. Okay, so some very tricky stuff there, I think. Not easy, it took me a while to wrap my head around it, but sort of geometrically, you can see what's going on. Over here, we have the answer as well. And so you end up with these three sort of planes that are intersecting in interesting ways. And you notice both of those planes, the blue and the sort of purple one, both go through this line, which was our condition, right? Let me just show you that this one and this one also intersect at 30 degrees. So we end up with this nice geometry. The numbers are very awkward, so hopefully your CAS calculator can handle it, particularly this last part, because you end up with solutions like this. And to answer the question appropriately, you need to expand this, collect like terms, and then move things to the right hand side to get an equivalent solution to what it says in the question to find the values of A, B, C, and D. We've just let this solution just has the right hand side equaling 0. Okay, hopefully that clarifies in some way. Good luck. I'll talk to you soon.